Okay, class, today we will be discussing all about the procedure on how earthquake analysis is being handled by the code provisions on the National Structural Code of the Philippines. And before I give you the details on that, I'd like to give you an introduction on how the analysis of structure differs from one another on the basis of linearity, nonlinearity, elasticity, and inelasticity of the material and the geometric property uh, of the member or the structure is concerned. Okay, so basically the analysis is divided into two: the linear elastic and the non-linear inelastic. For the elastic and the inelastic consideration of such procedures, we try to recall our force deformation characteristic, okay? Wherein at the initial stage of the structure's behavior, the graph of the force deformation or the stress-strain relationship actually is linear in nature. If not almost linear, it's actually uh, behaving in a linear pattern such that at this elastic stage, your analysis becomes linearly elastic. But there are also some materials which behave elastically at the same time, non-linear in terms of the force deformation. But considering steel and concrete, this basic assumption is actually very accurate. So beyond the range of the linear elastic stage, we have actually observing a sudden change in the curvature such that at this stage your a member or your structure behaves in a fashion wherein the curve is no longer linear and at the same time exceeding the elastic range. So this is now the nonlinear inelastic consideration. And to branch out several popular procedure on how to deal with the linear elastic and the nonlinear inelastic, we have these four uh, procedures that normally we see on code, no? On code specifications that are serving as the guide for structural engineers to deal with the earthquake design and analysis. And the most popular is of course the first one here, which is the static lateral force procedure, which is a purely coded code-based procedure, very well described in the NSCP code. Okay, This is the basic procedure that we need to know in order for us to be able to analyze the structure. And since this has some limitation, we can now expect these three other procedures to handle those cases wherein the static lateral force procedure cannot uh, handle, uh, such as this pseudo-dynamic lateral force procedure, or very popularly known as the response spectrum analysis, or the RSA uh, procedure. Okay, for the advanced procedures on nonlinear and inelastic, these two are the most popular, wherein the first one is actually a nonlinear uh, but static pushover analysis, in the sense that the computation involved is not done in terms of the time dependent modal analysis, but rather the time element is not considered, such that this static pushover analysis is a simpler method than the modal time history analysis, which is a little bit complicated. Now, for the static lateral force procedure, these are very well used for investigative purposes, including performance-based design procedures. Uh, while this RSA and this uh, static lateral force procedure are used more on uh, the design mode of such earthquake analysis. So for the modal time history analysis, the problem on this, which is the data that we are going to use in the history, uh, and that is quite difficult to extract, because some, not some, but most of the data on earthquake are not available for us. Okay, so for the static lateral force procedure, our basis for such is purely the National Structural Code of the Philippines. And this is a code-guided linearly elastic procedure wherein the forces are applied statically into the frame, assuming that the frame is an SDOF system. Okay, so this is a single degree of freedom system, meaning to say that the mode uh, uh, the mode used in the analysis of the building behavior due to earthquake is the fundamental modes only. Okay, so all modes are now based on the fundamental frequency and period of the structure. For the pseudodynamic lateral force procedure, which is the response spectrum analysis method, the vertical distribution of the earthquake are no longer based on the uh, procedure given by the code, but rather on the modal mass participation factor, and of course the stiffness also affects such modal behavior. So the analysis is still considered static, in the sense that your actual analysis is based on the conversion of your dynamic procedure into a lateral force requirement that will be used for your uh, structural analysis. Okay, the word pseudo here means that it's not a true, no, it's a false dynamic analysis. It's a dynamic analysis in disguise, or maybe vice versa. It's a static lateral force procedure in disguise. So the only difference is that here you become modal, meaning to say your modes are maybe considered in terms of three modes, two modes, four modes, etc. So for the static pushover analysis and the modal time history, unfortunately we will not be using this or considering this because these are advanced uh, concepts on structural analysis. And the modal time history analysis is actually the true dynamic analysis because we take into consideration the multi-degree of freedom system in computing for the displacement response based on a specific earthquake history data which considers your time element uh, in your analysis. Okay, so that's why it's dynamic because your response is actually a function of a given time. So let's not now start and focus on the code provision for seismic forces, which is in which the reference code I use here is the National Structural Code of the Philippines 2015. For the static lateral force procedure, the base shear is actually given by the formula 208-8, which is CVI over RTW. Also a derivative of the old formula that we can see as far as the old structural code of the Philippines is concerned. So this is the CIC over RWW, and V is equal to ZIKCSW, where CV is the seismic coefficient as set forth in table 208-8. NV is the near source factor as set forth in table 208-6. I is the importance factor in table 208-1. R is the overall strength and ductility factor of the lateral force resisting system. T is the elastic fundamental period of the vibration of the structure. And W is the total seismic dead load defined in section 208.5.2.1, pages 2 to 214. Okay? So equation 208 need not exceed the following. So this equation has a limitation on the use because we cannot overestimate or underestimate the base shear. So we need to use it only on the range in which your equation is actually applicable. So the code gives us now a maximum value. Okay, so this is the maximum value and the minimum values here. Okay, so this is the maximum, this is the minimum, where in this and these are used for specific purposes, no? So your minimum, this is the maximum, and this is the minimum, and this minimum value is used for both zones, no? All zones, and in addition to this minimum, there's another minimum value here, which must be checked on zone 4. So when you are on zone 4, you have to check it on this two formula here. Okay, where CA and NA are simply coefficients of a seismic that can be found on table 208-8, and NA is the near source factor that can be found on table 208-5. Okay. So these are the tables you can extract from the NSCP: 28-5 for your NA, 28-6 for your NV, and for your CA. Okay, so you have 208-7 and 208-8 for your CA and your CV. Okay, so I think we have to correct this. CA is 28 dash tama. 28 dash 7, I think. Okay, so this is 28 dash 7 and NA is 28 dash 5. So please correct this. CV is 28 dash 8 and NV is 208 dash 6. Okay, the near source factor is based on the linear interpolation of the values for distances other than those shown in table. So if you come up with a value in between 2 to 5 kilometers, then you want to get the value of NA at seismic source A, so you have to interpolate in between, okay? So I made a program on how to compute for this, and I'll share it with you. I did it in MathCAD. I'll show it to you later. Okay, so for your occupancy factors, the reporters have given us some overview of this, but I don't know if it's based on NSCP 2015. So for essential facilities, we have this seismic importance factor I and IP, wherein I are actually the main structural elements, and the IP are for the non-structural elements or the panel elements that we attach on the main structural systems. Okay, of course we have to concentrate more on the main structural system, so we have to look into these values here, but basically they are just the same except for hazardous facilities. So the definition of essential, hazardous, special, standard, and miscellaneous may be derived from the National Building Code, or it can actually be very well interpreted by the engineer on the basis of how essential, how hazardous uh, your structure is. For special, standard, and miscellaneous, we don't care about it because it's all one, no, point zero. Although in certain cases, this category occupancy description are important because some factors related to this factor I may be different. Okay, but in this case, I for special, standard, and miscellaneous are just the same. So we have to concentrate more on whether your structure is essential, hazardous, or not. Okay, so essential facilities are those which you think are very important in case disasters comes in. No, so like hospitals, like fire stations, like water tanks. Okay, so those are essential facilities. Okay, while hazardous are those facilities which, if not really uh, maintained on the basis of safety or designed particularly on the basis of safety, might affect the welfare of the uh, the occupants, or maybe the people around the facility, like nuclear power plants. Okay, uh, those which includes chemical products that can explode and cause fire, maybe. So the word hazardous there can be seen Uh, the definition, the technical definition can be seen on FEMA, on other code guidelines, but considering engineers' judgment, you can actually make use of your own way on how to categorize your facilities in terms of essentiality and hazard. Okay, for the structural system coefficient R, or I call this actually the ductility factor R. This is based on the type of system or structural system you have. Okay, and the most popular, of course, aside from those system that was defined by or reported by you, are the moment resisting frame and the dual system. Okay, so these two here and or these three here are the ones that are very popular. Although in some regions, this building frame system is also very popular, no? But in the Philippines, the MRFS and the dual system with intermediate moment frames are the ones. That's why you can focus mainly on these, okay, factors to consider for your value of R. And omega O, on the basis of the earthquake, maximum earthquake computation, you can see that these are all the same, 2.8. Okay. So for the building limitation, it's to height. You can see here if there's no limit, and NP, if this is not permitted. Okay. So you just take a look at the restriction on this based on the guidelines set forth by the National Structural Code of the Philippines. Now, for other types like steel structures, we also have here the building frame system and the moment frame system and the dual system. Okay, so the tube frame system, the other frame system you discuss on your report, are actually beyond the scope of the National Structural Code of the Philippines. So it has some important provisions that you have to see it before you can use it, because those structures are actually used for the design and analysis of skyscrapers or very tall buildings. Okay, so for the seismic zone coefficient, we will be discussing this on the next video that I will be presenting to you. But for the meantime, let us first address some of your concerns if there are questions before we proceed with the next video. Thank you.